My name's Sasha Hinkley. I'm a professor at the University of Exeter here in the UK. I'm originally from the United States, and I'm going to tell you more about direct imaging of extrasolar planets. And I know this is a pretty diverse audience, so I've really chosen to make this a very broad overview about big questions in this field. So forgive me for those experts in the room that might find this a little bit maybe on the basic side, but I work in the area of exoplanet direct imaging, where we're trying to spatially separate the light of a very faint exoplanet from that of its host star. And here's some of the best examples. We have the HR8799 system here on the left, as well as the Beta Pictoris system here on the right that I think Jane mentioned. That's sort of a 24-million-year-old star with a sort of nearly edge-on planet that we've directly imaged in this system. So we're only sensitive to the intrinsic thermal emission of these planets. We're not at reflected light yet, as the questions showed. We're really sensitive to these outer architectures of planetary systems, tens of hundreds of AU, and I'll draw your attention to those scale bars on there. But the real advantage of getting these photons directly from the atmosphere of the planet is that we can do direct spectroscopy. And this really gives us a window into atmospheric abundances and detailed characterization. But it's very technically challenging to do this. But nonetheless, many people have been working very hard on this, and we sort of have this gallery of directly imaged objects shown here. This may not be all of them, but we're kind of at the level where you can fit the number of directly imaged planets on one PowerPoint slide. And that doesn't really give credit to the sort of many surveys that have been trying to detect these things. And this is both an interesting plot, but also a bit of a depressing one for me. This shows the planet occurrence rate that have been derived for many surveys over the past sort of 10 to 15 years. And early on, we sort of had upper limits up here at sort of 10 to 15 years ago. But as time goes on, I think we see a downward trend in the occurrence rate and much more precise measurements of the occurrence rate of these wide separation warm young planets. So I think we can all agree now that the frequency of these is probably on the few percent. So it's been a tough 20 years, to say the least. And I should say that in the previous gallery I showed you of the directly imaged planets, many of those observations were taken with sort of existing workhorse instrumentation with some configuration to allow these very challenging observations to happen. But now there's a set of dedicated instruments to do just this: adaptive optics, coronagraphy, high contrast imaging. The most notable is SPHERE, shown here at the lower right. This is an amazing instrument. It's really many instruments in one. This instrument weighs 10 tons, and it's been a huge success for our field. The GTO survey for SPHERE, actually, the first discovery of this from this GTO survey was HIP 65426. So this is an A star, young A star, and you can see the directly imaged planets separated from the host star there. This planet is about 90 astronomical units, so it's a reminder that we're really probing a different kind of parameter space. But nonetheless, by spatially separating this light, we can get photons directly from the atmosphere, and we can get these gray sort of spectroscopy shown here compared with some models and some empirical measurements as well. But we're really only so far been sampling the 1 to 2 micron region, where we're really not sampling the peak of the exoplanet blackbody distribution for these objects that are sort of at 1,000 or 1,500 Kelvin. So this is our first major problem that that's been challenging us in this field for the past few years. We have really narrow wavelength coverage, and we have fairly low spectral resolution. Spectral resolutions of kind of like 50. And I hope you can tell that this is changing, and I'll tell you in a moment. We typically tend to observe young stars because the planets are brighter, and that makes our task a lot easier. So this is a plot showing the luminosity evolution versus time for a 1, 2, 5, and 10 Jupiter mass object. And you can see, I think, that at sort of older solar system types age, these theoretical models agree very well, but at the younger ages, these are quite divergent. They're quite discrepant. And so a second problem is that if we really want to constrain these models and move the field forward, we really need a larger sample of planets to fill this diagram, and importantly, they need dynamical masses. It's important that we don't actually measure a mass in direct imaging. We can only infer a mass, usually using a precise age. So nonetheless, we have this now demographics of planetary systems. Anders showed a similar plot where we have the radial velocity and transiting objects in sort of close at a fraction of an astronomical unit, but we have this wide collection of directly imaged objects up here. But I think it's clear from this diagram, the lower right-hand corner is highly incomplete. We currently don't have any directly imaged planets below about 2 Jupiter masses, and this is just due primarily to our sensitivity. Another thing is that directly imaged Venuses and Earths are so far quite out of reach, but Jane mentioned this. So since I don't know many people in this audience, I know some of you, I wanted to just mention my background very quickly. I'm actually very much an experimentalist. I'm an observer and experimentalist. Much of my PhD work at Columbia was dedicated to building this instrument there shown on the right. You can see me filling it up with some liquid nitrogen. This instrument actually started here at the IOA. And so we then brought it to Palomar Observatory. And then I continued work at Keck and VLT. But one of the things that's been taking a lot of my time over the last many years is that I'm PI for one of the JWST early release science programs. So with that in mind, I just want to highlight three fundamental questions that I think the direct imaging technique is really well poised to sort of answer. The first one has to do with atmospheres of exoplanets. And simply put, I think a real quest in this field is to ask, how can we directly link our measurements of atmospheric composition with a formation history? Everybody would like to do this. The second one is about these early thermal histories that I alluded to before. And I'm really curious about what do the early thermal histories of planets tell us about the process of planet formation. I mentioned that these models agree very well out of here at sort of gigayear type ages. That's so strange. Are we back? We're back. But here at the youngest ages, these models tend to really disagree quite a bit. And this is just due really to the intrinsic, this is just due to the basically loss of energy due to accretion shock physics early on in the planet formation process. The last one, of course, is related to Earth-like planets and this question of how can we begin to directly characterize such objects. So Jane gave a very nice kind of introduction to this. So let's get started talking about atmospheres very quickly. I mentioned that we'd really like to get more into the infrared, more in the sort of 3 to 5 micron range where these planets have the peak of their emission. But this is a set of observations from some very dear friends of mine, truly heroic observations trying to directly image exoplanets from the ground at 3 to 5 microns. And I think you'll agree that these detections are pretty marginal. And this is just due to the very, very high telluric background due to the Earth's atmosphere. So prior to JWST, we can take that even further. Prior to JWST, exoplanets had never been directly observed at wavelengths longer than 5 microns. And this is changing, of course, with JWST. And one of the early missions of JWST were the so-called early release science programs, where Space Telescope wanted to see entire communities organize to basically test drive this observatory early on to determine what are the optimal ways to operate this telescope and make clear recommendations back to the community. So I started getting the direct imaging community organized for this back in 2016, and I really want to highlight the work of 3 early career people. Brittany Miles here, who's now at the University of Arizona, my former PhD student Aaron Carter, who's just landed a permanent job at Space Telescope, and also some of you might recognize Shrishmoy Ray, who did his master's here at Cambridge. So Cambridge has had a big influence on all this. We had 55 hours of DDT time with this early release science program, but we only observed 3 targets. One of them was the HIP 65426 system that I mentioned earlier, shown over here on the right. This is perfect for coronography. It's a wide separation planet. The other system that we studied was VHS 1256b. This is another wide separation planetary mass companion, but it's at 8 arc seconds, so it's really not suffering from the contamination from the host starlight. We also observed a circumstellar disk, which I'm not going to mention in this talk at all. But one of the things that we learned very early on in the mission, which is very good news, is just about the stability of JWST. It's interesting because JWST in many senses was sort of designed to be this very stable infrared telescope with a lot of cosmological applications, but it turns out that's perfect for exoplanet science as well. So just to demonstrate that a little bit, these are a set of wavefront maps obtained only 2 days apart, showing RMS deviations on the order of a few tens of nanometers. And this right panel here is actually the difference between those two. So a derived drift rate of the wavefront error, the stability basically, is about 120 picometers per hour. So I'm delighted that we're measuring the drift in the optics of JWST in terms of picometers. This is just brilliant. It means that JWST is very, very stable, and that means that we can calibrate our observations very, very well. And that stability really has allowed us to deliver what are the first direct images of an exoplanet with JWST. So here's an image of that HIP 65426 system. We can see the coronagraph is in place, but there's still a tremendous amount of residual scattered starlight. And removing that, we actually see clear evidence of the exoplanet here with the 6-fold symmetry. When we do the same thing at 11.4 microns, we see a different pattern of residual scattered starlight, but then a very clear detection of this extrasolar planet here. And this is remarkable because this is the first time we've ever seen planets at these sort of wavelengths at all. But what we'd really like to do is we'd like to get dedicated spectroscopy. And we were also able to obtain the first direct spectrum of a planetary mass companion with JWST. And this is what it looks like. It's stretched from just basically 1 micron all the way out to 20 microns. And looking at the previous measurements are sort of in here. So this is a remarkable spectrum. It's just testimony to the incredible power of JWST, the enhanced spectral resolution, the sensitivity. We see evidence for carbon monoxide, water, methane, the usual suspects. But I was really excited about the detection of silicates, the direct detection of silicates that have been hypothesized to be there. But we see a clear detection of that. So just zooming in on the spectra a little bit, this is the kind of quality of spectra that we're getting from exoplanets. These are direct spectra. The CO band head opacity is there shown in pink. And so this long wavelength coverage, allowing us to sample multiple spectroscopic features, will give us much more precise abundances. And this is really going to allow a detailed comparison between transiting and directly imaged planets. So I want to turn to the thermal histories a little bit that I mentioned a moment ago. I showed you this sort of sad plot showing that the occurrence rate has been very, very low for directly imaged planets. And I think we now know why that is. And it's frankly that we haven't been looking in the right place. Taking a page from the radial velocity surveys, the radial velocity surveys are telling us that the frequency of planets probably has a peak around 3 astronomical units or so. It peaks around 3 AO and then turns down. And this probably coincides with the position of water ice lines for sun-like stars. But most conventional direct imaging instruments really can't reach these orbital separations of 2 to 5 AU. We really need sensitivity on the order of the diffraction limit of an 8 to 10 meter ground-based telescope. We can sidetrack that while we wait for the ELT with the VLT interferometer here, where we connect 4 8-meter telescopes together, and we can use this gem of Paranal called Gravity, which is just a remarkable instrument that is a K-band instrument that actually can do off-axis interferometry and measure the positions of exoplanets directly. So the Beta Pictoris system I showed you a moment ago, we see this clear detection of the Beta Pictoris B system. But precision radial velocity studies of this system indicated the presence of an additional planet, this sort of signature here. And I want to highlight the work of Matthias Novak here at Cambridge that really led this effort to detect Beta Pic C, which is a much closer planet orbiting inside the orbit of Jupiter at about 2.7 AU. So this is remarkable because now we're starting to sample that peak of the radial velocity distribution. And this is only going to get more powerful with Gaia. Gaia, in a few years, is going to give us thousands of detections of planets and hundreds of accurate orbits. An example of using Gaia early to sort of benefit the direct imaging method is maybe given by this study of the HD 206893 system. This was a target of the Sphere GTO survey that detected this kind of wide separation brown dwarf here. Shown here, it's sort of 20-something Jupiter masses. And precise astrometry has allowed us to follow the orbit of this outer brown dwarf, but comparing the Hipparcos proper motion of this star with the proper motion from Gaia indicated that there's an additional planet in here. And we indeed went after that with gravity using all 4 UT telescopes, and we found HD 206893c. This is a planetary mass companion at 3.5 AU. So again, we're starting to sample this peak of the radial velocity distribution. We're starting to bring these two techniques together. And just to give a sort of highlight of the sort of astrometric precision that gravity is delivering, these are magnifications of the orbits of these planets shown here. This has 50 to 100 micro arcsecond precision. So tracking this planet only over 2 months has really allowed us to measure a precise dynamical mass for this system. So this is a really powerful moment because when we then think about these populations of different planets, here I'm showing now effective temperature versus semi-major axis, but we have the transiting planets here at a fraction of an astronomical units, the directly imaged planets at wide separations out here, and this blue shaded region really shows the peak of the radial velocity distribution here. And putting our detections on there with Beta Pic C and HD 206893c really shows us that we are really sampling this. So this is great. Now we know how to unlock this hidden population of extrasolar planets. We now know how to get dynamical masses. So this is a really great moment. So I want to maybe just turn my attention now in the last minute of my talk to Earth-like planets, which I think a lot of people are curious about. Jane gave us a nice introduction to this. I think we're all probably aware of the decadal survey recommendation for a mission to fly in the first half of the 2040s. And that's a long time to wait for imaging and characterizing extrasolar planets. But I think we can actually have a shortcut with the ELT, and this is a nice CGI image of this observatory, but I want to make sure everybody's aware of the progress. Jane showed herself standing in front of it, but the progress is truly remarkable. METIS, as Jane mentioned, is one of the first generation instruments. This is the only instrument operating longward of 2 microns. It will have advanced coronagraphy and AO, but it'll also have a resolution 100,000 spectrograph at 3 to 5 microns. And this is the UK's primary contribution to this. Since METIS can operate at 10 microns, this is a very powerful opportunity to characterize the nearest Earth-like planets. So this is a plot of a spectral energy distribution of a sun-like star, shown in black there, as well as a simulated spectrum of an Earth-like planet. And we see very clearly this reflected light component, as well as this intrinsic thermal emission that's coming up at about 10 microns, just as the Rayleigh-Jeans tail of the host star is coming down, meaning that the contrast gap between these two is about 10 to the 6, and that's achievable. We're doing that now. There's no reason that we can't do this at 10 microns. So simulations that were done by Olivier Absil in Liège has dropped in a simulated Venus and a simulated Earth for Alpha Cen A in a simulated 5-hour observation at 10 microns, showing that in the absence of water vapor seeing, which is probably going to be our biggest obstacle to this, we can get fairly high signal-to-noise detections of these terrestrial planets. The worst case scenario with full water vapor seeing looks something like this. So this is kind of a best case, worst case scenario, but that's not so bad. Real life will be somewhere in between these two, and that indicates that the direct detection of terrestrial planets is potentially within reach with the ELT, which is not so far away. So just some final thoughts to leave you with. We've talked about atmospheres and that JWST is really delivering this much higher resolution and high sensitivity spectra. This will allow us to access multiple species in the atmosphere for detailed characterization. We also talked about that aspect of early thermal histories. I firmly believe that this is the most direct way that we can directly constrain models of planet formation observationally. If we look at the early thermal histories of these planets, provided we have dynamical masses, but now we can get those, and now we can get to the peak of where the planets are. For Earth-like planets, this may be a reality in the next few years with the ELT. So I'll leave it there and take any questions if there's time.